Hey there, in this lecture we're going to talk about regression and correlation methods. Learning objectives in this particular section will be describing the linear regression model, stating the regression modeling steps. We're going to explain the ordinary least squares method. Also going to see how we can compute regression coefficients. Furthermore, we're going to understand and check model assumptions as well. And in the end, we're going to how to predict the response variable. Another important thing would be to comment of SAS output. We'll see what is this and we'll also understand what this is about. So in the end, we'll have correlation models, link between correlation model and a regression model. And also we're going to see the test of coefficient of correlation to see how we can obtain that. So let's talk about models. So what is a model? A model is a representation of some phenomena. It is also known as the representation of non-math or stats model. So that's how we're going to use it in that particular context. Any phenomenon, any explanation or representation of a phenomenon is done by using a model. And the same goes for using stats model or non-math model as well. So let's talk about the maths and stats model. They are used to describe relationship between variables. And there are basically different types of maths and stats models. We're going to divide them into two types. First, they are deterministic models, and secondly, there are probabilistic models. Deterministic models are the ones in which there is no randomness. And there is no probability involved in it, which means that the answers are deterministic and no external factors depend on them. The probabilistic models are the one in which involve probability and hence they involve randomness as well. So let's talk about deterministic models. Deterministic models hypothesize exact relationships. They're suitable when prediction error is negligible. Also, the example for that would be the body mass index. It is a measure of body fat based. So the metric formula for the BMI is weight in kilogram divided by heights in meters squared. So you can see that the non-metric formula for this would be the weight pounds into 703. So deterministic models are fixed. They understand, hypothesize exact relationship between variables, and so they are quite fixed. They are deterministic and the answer is definite. So the weight in kilograms and the height of a person, there is no random element involved in it. They are facts and they need to be measured and quantified, and after putting it in this formula we can calculate the body mass index. So a body mass index formula is an example of a deterministic model. So the non-metric formula for the body mass index would be the weight in pounds into 703 divided by height in inches. Let's talk about probabilistic models. Probabilistic models basically hypothesize two components: deterministic, random error. So what an example of that would be the systolic blood pressure of a newborn is 6 times the age in days plus random error. So there is always some sort of error involved in the prediction of a particular variable whenever we're talking about probabilistic methods. Probabilistic models are usually involving with deterministic and random error. So considering this example, apart from the variable of time, we're going to add some random error in it because there is a possibility that it might exist. So in order to hypothesize these two components, we use probabilistic models wherever there is a random error involved. The formula for that is this. And it's also important to note that random error can be also due to many other factors rather than age. So if we're talking about random error in age, as considered in this example, so if there is a random error can exist in any deterministic variable, considering that it makes sense and relational to the problem domain. In this example, we have age in days, so there's a random error exists in that. But if we were using any other factors like birth weight, the random error can also exist in that as well. So there are three types of probabilistic models: regression models, correlation models, and other models. Basically, we're going to talk about regression and correlation models, and we're going to look into them and understand them as well. So let's talk about regression models. Regression models are used to represent the relationship between one dependent variable and one explanatory variable, or multiple explanatory variables. Another name for explanatory variable is the independent variable. So what regression models do is they hypothesize and they model the relationship between dependent and explanatory variables. So they basically use an equation to set up the relationship. Numerical dependent, also known as a response variable, one or more numerical or categorically independent variables. So this is the equation will be set up between these two variables, and we're going to use that equation to represent that relationship. Basically, mainly regression models are used for two things, prediction and estimation, as we will see later on. So the steps involving regression modeling are: firstly, we're going to hypothesize the deterministic component, in which we're going to estimate the unknown parameters. And secondly, we're going to specify the probability distribution of random error terms. So it's important to remember that the regression models are a type of probabilistic models. So probabilistic models hypothesize two components, the deterministic component and the random error term. So after we have hypothesized the deterministic component by estimating the unknown parameters, then we will move on to the specifying the distribution, a probability distribution of random error term. In this way, we will need to estimate the standard deviation of error. Third step would be, when we've done these steps, we're going to evaluate the fitted model. The fitted term comes from the fact that when we will use this equation to represent the relationship between these components, and we're going to evaluate. So, and after that we've done, so the term fitted comes from that. So after we have used the equation to represent the variables, after we've done that, then we're going to move on to the evaluation step. After we have evaluated, we're going to use the model for prediction and estimation. That will be the final step. Let's talk about model specification. In model specification, we're going to specify the deterministic component. Firstly, we're going to define the dependent variable and the independent variable. These are a part of the specification of the deterministic component, so the dependent and the independent variable. Secondly, we're going to hypothesize the nature of relationship. The expected effects, which will be measured by hypothesizing the nature of relationship, will be dependent on the coefficient signs, which will tell us the nature of relationship, as we have studied in correlation. But I do not want to confuse the methods. But a good example analogy would be that we use signs to represent the positive and negative relationship between two different variables, and we're going to use the same concept over here as well. So the functional form of that equation will also give us a lot of information. For example, whether the function is linear or non-linear will tell us a lot about the nature of relationship, and it will help us in modeling the solution as well. The interactions are basically we're going to understand, and they involve the prediction step where we're going to interact them with different variables, and we're going to see how our function or equation performs under those interactions. So the model specification is based on theory. Theory of field, for example, epidemiology. So it is entirely based on theory. Secondly, it's based on mathematical theory and the previous research that researchers and scientists have conducted. And fourthly, it's common sense. So the common sense part should be quite appealing to you. So it is quite logical, considering that we're going to model different relationships, and some relationships between different variables are quite simple and quite logical, and they're quite easy to understand. For example, apart from everything, let's talk about the price of houses, and as their prices increase with their size of the house. So it's pretty common to that if we've taken the data set considering from a particular country, from a particular state, and then we move on to the fact that we need to model the relationship between the house size and the price of the house. So if we buy a bigger house, it's going to be more expensive. So that's simple logical explanation. So that's why the fourth point tells us that it is common sense to understand regression models. So let's take this thinking challenge. So which is more logical? Let's talk about the different types of regression models. So regression models can be divided into two broad categories: simple regression models and multiple regression models. And furthermore, we're going to divide the simple and multiple regression models into linear and nonlinear functions, which will define and tell us the functional form of these models. So let's talk about the linear regression model, the simple linear regression model. So linear equations, let's start with that. Every linear equation has two particular things. One is the slope, which is defined by m, and the second is the y-intercept, where the line cuts the y-axis. So these two particular, you can say, this information, the slope and the y-intercept, enables to model the linear equation and gives it its shape. So the linear regression model is the relationship between different variables that have a linear function. So the linear regression model is used to represent the relationship between variables in a linear function. So the y-intercept will be the population y-intercept, the slope will be the population slope, and another thing will be the random error. So the random error, the dependent variable and the independent variable. So we have these two variables, and then we're going to calculate the y-intercept and the slope and the random error consisting there, and then we're going to model the relationship using a linear regression model. So let's talk about population and sample regression models. So population and sample regression models, the concept of population and sample, we've discussed that in statistics. And so the population, we don't know the relationship, so we're going to model it using the following equation. The E over here represents the error, the B, theta, and B1 are the y-intercept and the slope, just like in the linear equation. So we're going to see, and we're going to see the relationship between them using this equation as far as the model for the population regression is concerned. So the random sample, we're going to take a sample from the population, and then we're going to use regression on this. So the question over here is, the regression model used on the sample is actually equal to the population regression. So the same concept we have seen so many times in statistics and inferential statistics, that we take samples and we apply the normal distribution, and it is equal to the normal distribution of the population, given that we take enough sample sets greater than 30. So over here we're going to see the advantages of taking samples, a random sample from the population, since it is impossible to collect all the population data. So that we take a sample from the population and a random sample, and then we apply regression on it, and the relationship it gives us is equal to the relationship of the population if we were to model the regression. So the population linear regression model is basically represented by this equation. We have an observed value and the random error as well. So if we were to remove the random error and only use the two variables x and y, so if we were to model y as the expected value, then we would remove the random error and it would become only involves beta 0 and beta 1. So the random error is the distance between each observed point on the grid, and the distance from that to the linear equation, the line which is showing the relationship. So we need to minimize this error, and that's what we will do when we actually learn in machine learning, and by gradient descent we actually optimize the beta 1, the slope, by to reduce the random error. So that's what we do, and that's what we usually do when we're learning or training our machine learning algorithms in the machine learning part. So let's talk about the sample linear regression. We have the same components, the same values in this as well. So in this one, we have the random error to be, you can say, considering the sample regression model, it's not different from that, but as you can see, the slope is slightly different from the unsampled one because we have less observations. But we will later see that this is a better fit, and we will also understand what we mean by a better fit. But you can see that in a sample linear regression, we don't have to add the random error in the equation of the prediction value. So because the random error in the sample, we have a less random error as compared to that, and we will further reduce it as well. So let's talk about estimating parameters and least squares method. So we have studied scatter plot in data visualization. We know what we mean by that. So we're going to take two axes, x and y, and we're going to plot the xy pairs in the Cartesian plane by plotting these values. X will be the feature in or a column in a data set, and y will be our predicted value. So you can say that the y is the dependent variable and x is the independent variable. So given this particular graph, we have scattered points all over the grid. So how would you draw a line, and how well can a model fit? So which type of line can you draw given these points that you would call it the best fit? So let's take this thinking challenge and draw a line through these points. So the question is, how would you determine which line fits best? There are many types of lines, like given this one, and we can also have different ones, like everyone might have a different opinion. But do we have a metric or a quantifiable value which would tell us that this line given is the best because of this reason? So we need to think of something like that. But given the best fit, like, we will understand that, but the how can you draw a line that covers all these points and it is the best fit? So which line would be the best fit, and also how would you determine that the line is best fit? So the other example would be this line. So it is slightly different from the red line because the slope has changed and the y-intercept has unchanged, but this is a different one. So what would you think, that this is a better line or the red one is? But if you have an example, even if you have an answer, how can you back up or support your answer given certain proof? Then we draw another line which we have the unchanged slope, but we have changed the y-intercept. So we have three types of lines. We have the red line and the one which we have changed the slope but not the y-intercept, and the other one in which we have changed the y-intercept but not the slope. So given these three lines, which one do you think would be the best fit? And if not, do you have, or you can come up with another example. So in the third example, we have changed both the slope and the y-intercept. So now we have a different line altogether. We have changed both the parameters, the slope and the y-intercept, and we have a different line. So what would you think that is? Would you call this to be the best fit line? You see, it is rather confusing given all these three lines, and it's hard to say which one is the best. So that's where the least squares method comes in. A least square method is going to help us get the best fit line. So what we mean by best fit is that it is the difference between the actual y values and the predicted y values. So the difference between them should be the minimum. So best fit line would be the one in which all the y points on the line and all the other y points on the observed grid have a minimum distance between them. Okay, so we need to understand, we need to come up with a method that whenever we draw a line, it is drawn in a way that the predicted and the actual values have a minimum distance between them. So the predicted values are the one in which we are producing using the equation, and the actual values are the ones given us already in the dataset, which are plotted on the grid. So we're going to use the squares errors and we're going to minimize them. In this equation, it's pretty simple and obvious. We're going to subtract the actual value and the predicted value. We're taking squares because we do not want to end up with negative values. And so in the end, we're going to sum up all these squares and we're going to get a square errors. So the second step, after we get some of the squares, we're going to minimize this sum, and that is the job of the least squares. So after calculating the error, the difference, and the distance between the actual and the predicted value, we're going to minimize this difference, which is the sum of squared of errors. So graphically, what we're doing over here is that each E is the error, is the diff. So the actual values are the pinkish ones and the predicted values are on the blue line. So we're taking the difference, we're calculating distance between them, and we're going to minimize this using the LS method. And in the end, we're going to update the parameters of slope and y-intercept in a way that they will minimize the square errors. So that is the job of least squares. So let's talk about some maths, and we're going to see a couple of equations. We have the prediction equation, sample slope and sample y-intercept. So mathematics, as far as machine learning is concerned, it is important to have an intuitive understanding of it, but it's not highly necessary to learn to memorize all the equations because you can get them on the internet. You have Python libraries that have made your life a lot easier, but to have an understanding about these mathematical equations, it always helps in the long run. So let's start with the prediction equation, which is also known as the linear regression equation. We have beta 0 and beta 1. Beta 0 over here acts as the y-intercept, and beta 1 is the slope of the linear equation. But this is only possible, and these terms are only assigned as slope and intercept because only and only if there is a linear relationship between x and y. Otherwise, that would not be called as the slope or the y-intercept. So the slope, also known as the gradient of the equation, is calculated using this equation. We're going to sum all the different values, a difference of the product of actual and predicted values of x and y, and we're going to divide it by the square of sum of x values. So sample y-intercept, we're just going to change the location of beta 0. We're going to take it on the left side of equals to, and we're going to bring y on this side. And it's just, we're going to play with the first equation to get the intercept, sample y-intercept. So after that we have seen these equations, let's move on to the derivation of parameters. We have seen that the least squared methods, we need to minimize the least squares in order to obtain the optimal parameters for the line to perfectly fit the points. Now we have seen this, and in order to derive the parameters, we're going to take derivative of the least squares, and we're going to derive with respect to each of the parameters, and the result we're going to get will be similar to the intercept equation. So the derivation in the math is entirely optional. You don't have to go into the depth, but whenever we are going to minimize any particular variable, we will always take its derivative. So that's the takeaway from this mathematical derivation. So whenever we want to minimize something, we will always use derivative. So we're going to continue this, and in the end, we're going to derive both of the parameters, and beta 0 and beta 1. Beta 0 will be the y-intercept, because we only have two variables over here, and the functional form is linear. And beta 1, since it is the slope and gradient, so it will be equal to the gradient function. And this is the process to derive that. So the computation table makes it easier to perform all these equations. We take x and y, we square these values, then we also calculate the product. Any type of component mathematical function we need to perform, we will use this computation table to get it. It becomes rather easy, especially when you want to have a comprehensive approach. You can tabulate all the results, and you have all the results in one particular place. So let's interpret these coefficients. So the slope here, which is estimated by beta 1, is for each 1 unit increase in x. So what I mean by that is, if beta 1 is 2, then y is expected to increase by 2 for each unit increase in x. So the relationship over here is defined to be linear. If we're increasing x, y increases as well. But the beta 1 will determine how much this increase will be. If beta 1 is 2, it means that beta 1 will be multiplied by x, and the resulting y value will increase twice with every unit increase in x. So how we're going to interpret the slope coefficient beta 1. So the y-intercept coefficient beta 0 is the average value of y when x is 0. If beta 0 is 4, then the average value y is expected to be 4 when x is 0. So it's quite simple. If you take that beta 0 will equate to the y value if x is 0. Because in this way, it's rather simple, because considering the equation, the beta 0 will be equal to y if the x is 0. So the example of parameter estimation is something similar. So let's talk about an example for parameter estimation. So let's model the relationship between mother's estriol level and the birth weight of the infant child using the following data. We have the estriol level and we have the birth weight, and we're going to plot both of these values on a scatter plot. So now we have both these values. We have the x value for it to be the estriol level and the birth weight to be y. And now we're going to use the linear regression to estimate the parameters to get the best fit line for this grid. So first of all, we're going to use a computation table. We're going to take x and y values. We're going to compute their squares. We're going to sum these squares, and then we're going to sum these values to get these 5 parameters, and also the product of x and y as well. After that, we're just going to put these sums and products into this equation of beta 1 to get the y-intercept, and beta 0 to get the slope of the linear line. In this way, we're going to get the coefficients, and now let's interpret these coefficients to better understand how we can model them in the given domain of the problem. Slope beta 1 is the birth weight y is expected to increase by 0.7 units for each unit increase in estriol. So this is how we can understand, apply the concepts, apply the coefficients to the particular problem. So from the beta 1, we can learn that the estriol level the birth weight is expected to increase by 0.7 for each unit increase in estriol. So this gives us an important information, especially if we're going to estimate or predict in future what would be the birth weight of newborn baby. If we have the estriol levels, we can do that. So given the data, we have used the data to get these two coefficients, and now we're going to use these coefficients to apply the knowledge we have learned, to apply the knowledge in the future for the data we have not seen yet. So coming to the next coefficient, which is the y-intercept or beta 0. So this tells us the average birth weight of y is 10 units when estriol level is 0. So the intercept gives us the information average of the y variable. So it is always important. So you can get the average value by the intercept. If you have an intercept, you can get the average value birth weight. So this is the beauty, and this is the information you can take away from the beta 0. You do not have to actually calculate the average, and you can just look at the y-intercept, and it can give you the average value of the birth weight. Now there is something important here to understand. For this particular example, we have a negative y-intercept. As you can see over here, it is 0.10. So it becomes rather difficult to explain, especially when you're talking about the birth weight. Birth weight, since it is a numerical value and it is a continuous numerical value, and it cannot be negative, considering that if we're talking about birth weight cannot be negative. So this becomes rather difficult to explain, because the birth weight should always be positive.